trick for visualizing weather data and also using weather data in a different way to quickly look at the effects of different things like operating hours. So typically we've done our most simple energy models are simply a heat loss equation of some sort, and we use heating degree days to try to get an estimate of the energy use. But in fact, we know that a lot of these buildings are not constantly heated or cooled to a particular temperature, that it's variable and depends on occupancy. So we want to find a way to actually deal with that without having to, again, build an entire energy model because we don't have time for that and we may not have the data we need to do an accurate one. So it starts with getting the energy data. And I find a really easy way to get it is actually to use Climate Consultant to download the Energy Plus weather files. And so you can see here, I've actually already um, downloaded the weather file for Chicopee Falls and Westover, which happens to be the appropriate weather file, TMY3 weather file for the region we're working in mostly. So, and I've shown you Climate Consultant a little bit so you can see it's got a bunch of good information about the data. But what we really want to do is simply export the weather data. And in this case, we're just going to do, it's just heating, so we're really only interested in the dry bulb temperature, and we're going to do hourly weather data, which means we're getting every single hour for a year. And we can use that for a whole bunch of things, but in this case, I'm going to show you how to kind of assemble it into bins. Now, I'm not going to export the CSV because I've actually done it, but what happens is you're going to get a CSV, and in this case, I've pasted it into a tab in another spreadsheet, and it comes out very simple. It says Chicopee Falls, it's got the location, month, day, and hour for each of those hours, right? And then we have, now I want to know the day of the week because it's not enough to know what the month and the day and the hour are. We need to know, is it a Monday through whatever Saturday? And we're going to assume that in the case of the schools, that they're not actually occupied during Saturday and Sunday. Here, this one is in degrees Fahrenheit, is the actual weather data. Remember, we only wanted the dry bulb temperature, so that's all we got. But now, because we have the day of the week, and in this case, since this is not a real year, this is a typical model year, so it's taken 15 years worth of data and created a fake year that is really kind of like it's supposed to have typical characteristics of a year for this location. So because of that, we can just start the first day of the week, also of the year, is also a Monday. And so basically, I've created a very simple day of the week formula, which says if the day number is the same as the day before, then let's find out if it's then just we want to find out if that day number is less than 7, then it can just be the day before plus 1, right? So if it has just changed from 1 to 2, then we're going to name that day 2. Now these first ones, obviously December 1st happens to be a Monday, so it's a 1, and then December 2nd happens to be a Tuesday, so it's a 2. But once we get to these other days of the week, we need to generate that through, and so it multiplies by 1, and then it says otherwise just make it the same day because we're going for 24 hours. So simple formula that gives us a rough approximation of what day of the week it is. And remember, it's a fake year. It's not a real year. But the weather file, again, is normalized. Then we want to convert that into whether it's occupied or not. So here's where you can see this kind of complex if formula is referring to other cells on the other tab. So we've created this other tab where we're going to generate these bins. And these bins each refer to different temperatures. So I'm going to go back to the occupancy thing. So here, this is where I input the occupancy and I say, well, I think the school is open, or they start heating it up from 6 a.m. and they close it at 5 p.m. And you can see I'm using 24-hour clock, so 1700 hours. And then we say, well, it's occupied from day one, which is Monday, to day five, which is Friday. And we've put in the summer break, which is important because we're going to find there are plenty of temperatures below our building balance point that happen during summer, but we can assume that they're not heating. And in this case, I happen to know that they do not turn the heat on until October. And then we can do the same with the winter break. So we've put in these occupancy parameters, and then we have, like I said, a fairly complex if-then formula that basically just asks, essentially, if it's not any of these unoccupied hours, then give it a 1 for occupied. Otherwise, it's unoccupied. And one thing you'll notice is that a building like a school actually spends way more hours unoccupied than occupied. And that's going to have a big impact if we can adjust how they operate the building. So we can change the balance points and the set points. And I'm going to give you those inputs in a minute. But I also want you to see what we've done here. And this is creating what we call binned data. In this case, I've taken basically the high point of each bin is just 2 degrees apart in Fahrenheit. And because we're concerned with heating, we're really going to only be concerned with the temperatures below the building balance point. But so we're eventually going to get ourselves a histogram of the frequency of occurrences. So for instance, we can see that, if the bin is between 16 and 18 degrees, that is to say that the average bin is of that bin, the average temperature of that bin is 17 degrees, then the number of hours is a countifs formula, right? It's saying count all those temperatures in the TMY3 file, count all those hours if they are between those two temperatures. We count all of them, and then for our calculations, we're going to use the average the average temperature for that bin. So there is some imprecision, right? We're already clustering things together and taking averages, but it allows us to do some other useful things. You can also see that that only happens 1% of the year. And so that particular temperature. But you can see that certain other temperature ranges occur much more frequently, right? So, in the 49 degree as an average bin, so between 48 and 50 degrees, that's 5% of the year. So that begins to give us a sense of what's important. And so over here we can see this is basically that frequency distribution, right? It's a histogram of all the temperature bins cooler than the balance point, which this particular building in Northfield is 64 degrees Fahrenheit. It's pretty not great building, but we improved it a little bit. And so you can see a few things. First of all, you can see the frequency of these different temperatures. You can see that we get a whole lot of the time, a whole lot of hours in some very mild temperatures, right? If you look at kind of just visually at the bulk of all these hours, if we just look at the vast bulk, we'd say that most of the temperatures during the heating period are above 31 degrees Fahrenheit. So basically around freezing or a bit higher. And here I've got this curve which shows us the percent of all hours. So if we draw that line, we can see that about 84% of all the hours of the heating season, so 84% of all the hours cooler than 64 degrees Fahrenheit, are above 30 degrees Fahrenheit. So if we're thinking about the efficiency of heat pumps, and we know that they're actually quite efficient, have a coefficient of performance well above 3 at around freezing, then then we know that might be a good application in a location like this. The other thing you see is this load, and obviously it's a straight line because it's related directly to temperature. And so the building load, this is simplified building load because we haven't looked at occupancy yet, but as you can see, the building load, this spot over here with 100% of the load is actually colder than the design point. And what you can see is that never happens. Like that happens pretty much 0% of the time. And yet that's the temperature for which we're designing the heating systems. And yet we could design a heating system that, like a supplementary heating system that addressed 84% of the load. 84% of the time, it only addresses about, what would this be? This is about half, right? That's roughly half of the load. At roughly half of the load, we are covering 84% of the heating season. So it gives you a sense of why it might be worth it to keep in place, say, an old and not very good oil-fired heating system to pick up the load only when the say the heat pumps can't keep up with it, because that's going to happen at, let's say we say the heat pumps fail to keep up after 15 degrees Fahrenheit. Well, that means that for 97% of the heating season, the heat pumps are able to handle the load. So sure, let's keep that boiler handy to pick up the difference, 3% of the year. Whoop-de-frickin-do. And okay, so now we've got a chance to also, because we have these bins, we can make them both occupied and unoccupied. So here, now instead of just counting the frequency of the total number of hours that we experience these average temperatures, or the temperatures between these two things, we can actually go back to the other sheet and say, well, actually, for the unoccupied, only count them if they're between these two temperatures and it's occupied. And and then you find that for it's unoccupied here, sure, it's unoccupied. It's the middle of summer, but there are no times when you have a 98-degree Fahrenheit temperature and the building is occupied. Not surprising. And if we go down into the heating season, we can even see that, let's say it's 50 degrees, or between 40, so about 47 degrees. Well, it turns out there are about 47 hours when the building is actually occupied when it hits that temperature. But there are 229 hours when the building is unoccupied and it hits that temperature. And then we can say, well, this is from somewhere else where we did a regression analysis and we got the building UA. We basically regressed the actual heat use against heating degree days, and we calculated the building UA. We can now put that into the actual demand. So here's the unoccupied demand and the occupied demand, and we can separate them and then sum them together later. So here we're just simply, we'll take a low temperature here, or moderate temperature here. So you can see that we're saying if this UA times delta T formula is greater than 0, then just give me that that UA times delta T formula, because we're only looking at the occupied hours, right? So it's basically taking that, but it's looking at we're multiplying it times the occupied hours, right over here. And we do the same for the unoccupied hours. We've already calculated our number of hours at each of these temperatures in these bins. So that allows us to then take this information and we can do a bunch of things. So this school currently operates, its unoccupied set point is 62 degrees because they're really scared about freezing pipes. But the solution I proposed to them actually circulates water even if it's relatively cool, so that we basically eliminate the fear about freezing pipes, so we can actually lower the unoccupied set point. So right now, uh, we can see that their current use and proposed use are the same because we haven't changed the unoccupied set point. And basically what I did is I copied this proposed uh, amount of BTUs and pasted it as a value into the current use so we could compare them. But now let's just change the unoccupied set point and let's say, oh, we're going to get really aggressive and we're going to say the unoccupied set point will be 45 degrees Fahrenheit. Now it's calculating the differences, and obviously the delta T from 45 to whatever. In fact, sometimes it's going to be zero, like there will be no difference. It'll be 45 degrees outside, and the heating system simply will not have any reason to run. So we can see that in this case, we create a 48% savings just by that aggressive setback temperature because there are so many hours. And we're saving them, if we assume $2.10 per gallon, we're saving them for $14,500 just by changing a set point that's enabled by this system that I did. So the main thing I want you to take away is to be able to look at this histogram of the frequency of temperatures in each of these bins and realize how much of the heating season is actually very, very mild and can be satisfied with much, much less capacity than what all of these buildings have as their overall capacity. And of course, that's improved if we also reduce their heat loss. And the value of being able to create these binned data. And you can choose bigger bins if you want, right? I did 2-degree bins, but you could do a 5-degree bin. And by being able to use occupied and unoccupied temperatures, you can explore the effect of just one intervention. We could do the same thing. Let's say we were only looking at ventilation. We could calculate the heat loss on ventilation only when it's occupied, because that's when you'd be running your ventilation. And then we could see, well, what would be the savings if we put heat recovery on that ventilation. So I hope that's useful.